just to be clear for everyone, when we get a grant, we don't get that money. Like the grant is money, but what we do with that money is that we give it to we hire, people, we hire PhD students, we use it. It does not come into our pocket. That's not how grants work. So it's very confusing. It's very confusing. If you want to have a job with a high salary, indeed, if you have a physics background, you probably want to go into finance and not try to work your way up through UK academia, hoping that there'll be a high. That's just not really how it works.
The guest of today's podcast is Dr. Nabil Iqbal. He is a theoretical physicist at Durham University in the UK, and he majorly works on holography, generalized symmetries, and problems in condensed matter physics. In this episode, we talk about these topics. In addition, we also discuss science popularization and aspects of being a high-energy physicist. So let's start the episode. So first of all, Dr. Iqbal, welcome to the podcast. It's nice to have you.
Thank you so much. Thank you for having me. I'm really looking forward to our conversation.
Sure. Okay, so the first thing that I ask, almost every guest is that how they got interested in physics. So what inspired you to, come to physics?
So I guess part of it is that in fact both of my parents were educated as physicists, and in fact my mom is a physics professor at a university, and my dad was a computer science professor. And so for a very long time in my household, physics was just seen as a very normal thing to do. It was like a standard thing. It's like the family business. So I think that contributed a lot. But I think a real turning point for me, thinking of it as a really serious thing and not just something that people do, was when I read A Brief History of Time, Stephen Hawking's book, at a young age, just like 12 or 13. And that's just it's just a fantastic book, right? It's just full of so many amazing, beautiful things. And I read it, I loved it, and I thought I wanted to learn more about it. And then I just really leaned into that, and I kept learning more and more about it. And here I am.
I mean, I'm again very happy because whenever someone mentions that Brief History of Time is the book that got them into physics, I'm very, very happy because I think that's the book that got me into physics as well. About that book, so were there some topics that you didn't know existed before reading that book, or were you aware of the topics but the book itself was inspirational?
So it's been a long time, to be honest. I should read it again as a grown up. But I think that before that, I didn't really know about any of those things. Like I didn't know. It has some brief discussion of like special relativity and time dilation and black holes and all that stuff, and I just didn't really know any of them. And the book, I think, does an amazing job of sort of making you feel like this is both beautiful and something that is understandable. It does both of those things. And but I think going into that, I'm not sure I really knew any of the topics that were in there. Yeah.
Right. So would it be accurate to say that that book inspired you to come into physics, but it also inspired you to come into high energy physics?
Let's see. I guess probably, to be honest, because I always knew that I wanted to learn the things that were in that book, and that
Right.
I later learned that is high energy physics. I didn't know that at the time, but then I later learned that was high energy physics. So it was sort of a goal to keep learning physics until I could understand everything in that book properly. And I guess that path is what ended up with me going down high energy physics. So yeah, I think it's a pretty accurate assessment. Yeah.
Right. So, but I've seen some people who got inspired, to come to physics because of that book. But when they actually start to study physics, they get introduced to other topics and then they change their mind. So, did that ever happen to you that for some time you change your mind? You said that probably I will do something else and not high energy physics.
Oh, I kind of think this happens sort of for me. It happens like all the time. In
Okay.
that, I think it depends a lot who you hang out with and what topics they're interested in and talking about. I think for me, that sort of thing has been very influential. Like during my PhD, for example, I worked on AdS CFT, but I worked on applications of AdS CFT. So just for your listeners, AdS CFT is this amazing thing. It's this correspondence between quantum gravity and quantum field theory, and it's a really big deal in string theory and the study of quantum gravity. But at the time, I sort of studied how one could use that to think about problems in condensed matter physics, and condensed matter physics is something completely different from high energy physics, right? But thinking about these problems, it sort of I really got interested in condensed matter physics for its own sake as a result of thinking about things like that. And so this happens to me, I think, periodically, that I'm introduced to some other idea and I think, oh, I should really learn this and study this. And then if I have time, I try to study it. And sometimes I'm even lucky enough to be able to work on it, to write papers in it. And so for me, I think this happens all the time, basically.
Right. Yeah. I mean, one of the things that I wanted to go into is something that you have already mentioned, which is holography, right? So you have worked quite a lot on on holography, especially when you were a PhD student. So I want to go a bit deeper into holography because I mean, I am quite familiar with how the methods used in ADS-CFT, but I'm not very familiar with the applications of gauge gravity duality to condensed matter physics, for example. So, for the listeners, let's start from kind of the beginning, and let's talk about what is the motivation to consider something like ADS-CFT. So, I mean, you can use some jargon. That's fine because we will describe the jargon.
Indeed. Yeah. So I think that ADS-CFT, the main motivation is probably, I think, to be honest, different people have different ways of thinking about it. So I'll tell you how I think about it. And of course, your listeners should be aware that other people have other motivations. So for me, I think the main point is something like this. If you imagine that you're thinking about a theory of gravity, so a system that has gravity in it, then if you have something with gravity in it, gravity is an attractive force. And if you pile enough stuff together, then no matter what, in any reasonable theory of gravity, that stuff will pile together and form a black hole. And now we have to digress slightly and talk about the concept of entropy, which again, I think most of your listeners are familiar with. Entropy for any system is sort of a measure of the number of things that your system could be doing. Okay. So if you take an ordinary system, not a black hole, just take an ordinary system, like I'm drinking water. If you take this glass of water, then the entropy of the glass of water goes like the volume of the glass of water, basically because every degree of freedom in the water can be doing its own thing. Okay. That is how all normal systems behave. The entropy scales like the volume of the system. Now, there's something very special about black holes. If you look at a black hole, it turns out miraculously it's possible to calculate its entropy. And the entropy of the black hole does not go like the volume of the black hole. It instead goes like the surface area of the event horizon of the black hole. So it goes like an area and not like a volume. This is a very deep and profound thing because it sort of tells you that the physics of the black hole is somehow like the physics of something that lives in one dimension lower. And this is a recurring theme throughout ADS-CFT, throughout gauge gravity duality and all these correspondences. They tell you that somehow the gravitating system is equal to a system that has one lower dimension. And for me, that's the main motivation why something like ADS-CFT has to be correct at some deep level, because the black hole entropy scales like the area and not the volume.
So, I mean, the motivation that you have given can be thought of as a motivation for something like the holographic principle, right? But
Yeah,
ADS-CFT is more specific than that. For example, I mean,
yeah.
okay, the thing that you are talking about is the information living on, the area of the black hole, which is fine, which is, kind of the motivation of holographic duality. But how come one understand the motivation to have a connection between a gravitational theory and a non-gravitational theory? I mean, that's not obvious, right? From this black hole analogy.
Yeah, I would say it's not obvious at all. I think it's not obvious at all. And that's why the specific examples coming from string theory are so important. So what I just told you right now is a sort of vague, fluffy idea that suggests something like this might be happening. But the field really took off in the 90s when very specific examples were constructed. They're very specific, meaning it's a very precise theory. N equals to 4 supersymmetric Yang mills. It has this particle, that particle, this particle. You know exactly what particles they have, and it's exactly equal to a gravitating theory living on a particular space-time background. 80 is 5 times that's 5. And I think that's really important because it really put sort of flesh on the bones. You know, we had some vague idea, something that should be true. I think I wouldn't believe in specific correspondences if not for the fact that we really had these examples that are so precise, so detailed. Everything that you can calculate on either side and match is correct. So for me, I think the string theory examples are really important for this.
I mean, okay, let's go a bit deeper in this example so that the audience can understand. So, what you were referring to, correct me if I'm wrong. So, what you were referring to is that there is this theory called N equals 4 super Yang mills, right? And it lives on a particular membrane called D3 brane, right?
That's
And
right.
then you have gravity, on this particular background called ADS5 cross S5. S5 is just a five-dimensional sphere, right? And the thing is that in order for this duality to work in this example, you need a certain number of ingredients, right? You need something called the decoupling limit, and you also need something called large N limit as well. So how do
Mhm.
these things come into play? So I mean, again, you can use some jargon to explain this example. So how does this
Okay.
example, work in detail using these two ingredients as well?
Yeah, so that's a really good question. So let me answer that in two different ways. So first of all, in the early days of AdS-CFT, if you started to learn AdS-CFT, the way in which this would be described would be something like the following. You take an object from string theory, and that object is called a D3 brane, but the name isn't that important. And it's a thing. It's really a thing. You can imagine it like a sheet of paper, okay? It has some things living on it, some degrees of freedom living on it, which are basically particles. They wiggle around, and the theory that describes them is a kind of it's a theory which is called n equals 4 super Yang-Mills. But again, the name isn't so important. It's a theory of particles living on this brane. And then the way that sort of these introductory treatments to the subject would start would be you take this thing and you think about it in two different ways. You think about it as itself, as particles living on this brane, or you find a way to think about the fact that this brane lives in a gravitational world, and you sort of crank up the strength of gravity, add more and more and more branes, do various things to make these branes sort of curve the space-time background. And if you do that in the right way, if you curve the background in the right way, eventually you kind of lose the branes. You just get a curved space-time background, which should somehow represent the same physics. That curved background is this quantum gravitational theory living on a curved space. And again, the name of that curved space is anti-de Sitter space. And so this was sort of this is if you go to the details of this is the decoupling limit that you mentioned. And one can do this in great detail and really obtain a quantitative matching of parameters. Now, I should say that there's another way to think about it, which at least for me has been maybe a little bit more useful, which is that the decoupling limit is a way to obtain two different things from string theory, where one of the things is the quantum field theory and one of the things is the gravitational theory. But the fact that these two things are actually equivalent to each other is in some sense maybe deeper than the particular limit that we use to derive this thing. In this case, we had a decoupling limit and we could, tune these things to get these two things out of it. But I kind of think that the duality in a sense is philosophically independent of the decoupling limit. It's just the fact that these two things are equivalent. And that's the way I think about it now. The string theory gave us the sort of lamppost to figure out this duality, but the duality itself is maybe deeper than the decoupling limit from which it came. I don't know if that answers your question or not, but
I mean, to some extent it does, but someone may ask this question that, okay, I can kind of understand that why the ADS space-time is relevant here, but what is the role of S5?
yeah. So again, that's a very deep question, I think. So one sort of heuristic way to understand this is to think about the symmetry. Okay.
Mhm.
So let's go back to our field theory. Okay. Our field theory, the theory of particles, which is equivalent to the gravitational theory, that theory of particles, when you study any system, you should first look at the symmetries. And this theory of particles has an SO6 symmetry. An SO6, you can also call it SU4. Actually, one of those is more correct than the other. I think SU4 is the right way to think about it, but sorry, I'm now going into jargon. Think of it as an SO6, okay? And what is an SO6 symmetry? An SO6 symmetry is the set of rotations of a 5-sphere. For most readers, the case that'll be much more familiar will be SO3 rotations, which are literally the rotations of a solid body in 3 dimensions, which is the set of rotations of a 2-dimensional sphere. There's just a higher dimensional version of that. So on one side, we have an SO6 symmetry, and now we have to think about a way to realize that SO6 symmetry on the gravity side. And it's sort of very beautiful. Gravity really realizes it in what I feel like is a very intuitive way. It has a 5-dimensional sphere which realizes that SO6 symmetry. It really acts like rotations of the 5-dimensional sphere. It's a very obvious, very geometric thing. So that's maybe one of the sort of lessons that the duality tends to take symmetries and geometrize them. It makes them into aspects of the space-time geometry. And in many ways, that's easier to visualize than it was before you did this duality.
Right. I mean, you mentioned that on the field theory side, and to remind the audience that the field theory that we are talking about is n equals 4 super Yang-Mills. Does the 4 in n equals 4 has anything to do with SU4?
In some technical sense, probably, right? Let me think about this. I should be honest, it has to do with the supersymmetry, I believe. Yes, I think that it does, but it's yeah, the SU4 is what this is getting very technical. So let me avoid it and
It's
say
fine.
yes,
I mean,
it
it's
does.
fine.
It
I
does
mean,
have
that's
to
why
do
I'm
with it.
saying you
Yeah,
can use
yeah,
some jargon.
yeah. Okay.
So
It,
you're talking about
yeah,
something called the R symmetry, right?
exactly. Yes. I didn't want
Right.
to get into it both because it's technical
It's
and I try to avoid supersymmetry in my research as much as I can. Sometimes it's unavoidable, but But yeah.
Okay,
So
it's fine.
yeah,
Okay,
yeah,
so this example is as we discussed that it's one of the earliest example constructed in AdS CFT duality. So one thing that I mentioned earlier is that you need something like large N because the gauge
yeah,
group that exists on the field theory side is called SUN, and you need large N. Okay, so the thing is that it's fine if for that example you have AdS spacetime and you have large N. But I've seen that people use holographic duality or the gauge gravity duality to, solve problems in something like QCD, right? So how can you use, it to use QCD when QCD is neither a conformal field theory and you
yeah.
don't have large N there? So how do you use it to, solve problems in QCD?
Yeah, absolutely. So that's a fantastic question. So let me first for your maybe I could just for your listeners explain why large N is so important, and then we can think about how one is meant to make sense of the fact that we're using it in this terrible setting. Let me just so what large N means is the following. In my field theory, my theory of particles, a way to think about this is that each particle basically has a matrix attached to it. Okay, the matrix sort of measures the degrees of freedom of the particle. And the n that we are referring to over and over again is the size of this matrix. Okay. So what we're saying is that when you take this n, make this n very large, that means that every particle has a very, very large matrix attached to it, many, many numbers associated with this particle. And it's a remarkable fact that when you take this n very large, okay, then the theory that was very complicated, very strongly interacting, everything talking to each other, it simplifies. It becomes much, much, much simpler in this large n limit. And it's really not obvious that this should happen, but this is a recurrent theme in physics that when you increase the number of degrees of freedom, often life becomes simpler. And in fact, this quantum theory becomes, in a sense, classical again. By classical, again, I mean that even though everything looks like it's interacting very, very strongly and very quantum and very wiggly, there's a description of this quantum system in terms of some classical equations of motion. And it turns out these classical equations of motion that I'm talking about are exactly the gravitational equations of motion on the gravity side of the duality. Okay. So you should imagine that on the gravity side of the duality, 1 over n measures how quantum the gravity side of the duality is. Okay. So if n is very, very, very large, then the gravity theory is very, very, very classical. And that's great. We can understand the gravity theory, use that to understand the field theory. But when n becomes small, then the gravitational theory starts to become very complicated. It becomes itself more quantum, okay? And now we sort of stop being able to understand well the gravitational theory, and it's less useful to understand aspects of the field theory. Now, let me come back to your question. Does it make sense to use a large n expansion for systems where it doesn't really seem applicable? Like you mentioned, people use AdS CFT type ideas to study QCD. And for QCD, n equals to 3. Okay. And 3 is not an extremely large number. And so you should really ask, what are we doing? Why are we doing this? Does this make sense? And you see, it's interesting. In some sense, this maybe doesn't make exact sense quantitatively, but I think to give you a handle on the physics, it's very, very valuable. Basically, because in QCD, there is no obvious thing to expand in. You have to use every trick that you have, okay? It's crucial that as physicists, we use every trick that we can to understand strongly coupled systems, right? And QCD is one of them. So I think that's really why people use this so much, because even though it is not a controlled approximation to QCD, it's one of very few things that we have in our toolkit. And it is for many things much better than, for example, trying to study QCD as a theory of weakly interacting quarks and gluons. It's much better than that. One example that I think was very influential for me at least was to understand the properties of the quark gluon plasma. Okay, now the quark gluon plasma is a real thing. It's what you get if you take the theory of strong interaction to take a bunch of protons and neutrons or whatever and heat it up very hot. Okay, then the quarks and gluons will come loose and they sort of form a liquid called the quark gluon plasma. They interact with each other in a very strongly coupled way. And this liquid is actually very, very confusing. It is, in a sense, a perfect liquid, which means that it's very hard to calculate anything in it. Okay, but what you can do is study a different system using this holographic duality and ask, how does the liquid in that system look like? Does it look like the quark gluon plasma or not? And in some ways it does, and in some ways it doesn't, but it gives you a different starting point that you can think about the quark gluon plasma with. And so, for example, there's various measures that, for example, the viscosity of the quark gluon plasma was something that was very confusing. And the easiest way to think about the viscosity is to think not from a weakly coupled standpoint, which is conventional, but to think from an arbitrarily strongly coupled viewpoint, which is what you get if you study it using this holographic duality.
Right. Okay. So, um, correct me if I'm wrong. So, in the conventional, ADS-CFT correspondence,
Yeah,
in the ADS space-time, we have this coordinate, which is sometimes referred to as the radial direction, right?
yeah, that's
And
right.
and in this ADS-CFT correspondence, this radial direction corresponds to energy scales, right?
That's right.
So,
Exactly.
is it true that you have to truncate the ADS space-time in order to study QCD because you have this confinement scale?
Absolutely. Sorry. Sorry, Les, you asked your question at two parts, large N and conformalness, and I forgot the conformalness part. Let me just say a few words about this energy scale thing for your listeners. So,
Mhm.
again, this correspondence is simplest when you're thinking about this very special theory, which we've called N equals to 4 super Yang-Mills. And this theory has a SO6 symmetry that we talked about, but it also has another symmetry. It's what's called a conformal field theory. And what that means is, in a sense, that it has no preferred length scales. What that means is that if you have any object in that theory, in some sense, you can try to make that object bigger and smaller, and that's still a reasonable thing in the theory. There's no preferred scale. Okay, and that's interesting. The fluctuations happen at all scales equally, and you can again ask, how do we think about that symmetry on the gravity theory? And here, this is why the gravity theory has an extra direction, which again is sometimes called the radial direction. This extra direction, basically, you can think of as telling you where in energy you are. In other words, if you make something bigger on the field theory side, that corresponds to moving it in the extra direction on the gravity side. Okay? And again, this fact that the symmetry is now geometric is really helpful actually in understanding what's going on. Okay, so that's in this really well-known example of this duality. However, this is not true if you are looking at, for example, QCD. In real life QCD, it is definitely not conformal. Okay, the proton is an excitation in real life QCD. It has a size. It weighs 938 MeV. It has a size. It is not true that you can make the proton bigger and it'll be the same. It's just not true. It has a preferred size. And so what that means is QCD is definitely not a conformal field theory. That's in a sense the whole point of it. And therefore, if you want to study QCD using the ADS-CFT duality, then you have to find some way to incorporate that physics in this duality. And as you said, that means that you have to find some way to sort of change the geometry so that basically what has to happen is there has to be an end to the geometry at some point. And the reason why that is because in QCD, there is a lowest mass scale. It's called the mass gap. And there are no degrees of freedom that are lighter than that scale. And in a sense, the theory is therefore empty at very long scales. That must happen on the gravity side as well. And the way in which that happens is by capping off the geometry so that nothing exists past a certain point in this radial direction. So you're absolutely right. One has to find a way to cap off the geometry. And in any application to QCD, you have to ask whether the thing that you're doing to cap off that geometry, is that similar to the way that QCD does it, or is it different? Okay. And this is a very important question. And I think there's many ways to do this, and things are better at some examples than at others. But I think it's very important to note that in any application, you have to be really careful about the fact that if you want to study real life with this, you have to think about whether your infrared physics is really what you want to capture, whether it's really being captured in the right way. This is a very tricky point in applying this to QCD.
Right. So when you write down the Lagrangian of the QCD, it has a symmetry called the chiral symmetry, right? But
That's right.
there is this phenomenon in QCD called chiral symmetry breaking. So
Yeah.
how is that realized on the gravity side? Do you have to use a brain or something like that?
Yeah, there are various ways to do this. I think that the most well-studied thing is something called the Sakai-Tsukimoto model. And what that involves, basically, as you say, is it involves brains. Now, it's been a while since I looked at this. So I'm probably going to get the details in detail wrong, but I encourage all your listeners to read the beautiful papers on this. But what basically happens is you have brains that have degrees of freedom that transform in the symmetry in the correct way. Okay. And then the chiral symmetry breaking, if I remember correctly, has to do with the way that if you think in the gravitational theory, you have multiple brains, and these brains can either join up in the interior or remain disconnected in the interior. And when they join up, that corresponds to a breaking of this chiral symmetry. Okay. And again, I don't want to get too much into it because I worry I'm going to get the details wrong. But there's some beautiful work on this by Sakai and Sugimoto showing how, or they started it after that many people studied this, showing how in one specific model you can really think about symmetries very much like the chiral symmetries within this duality.
Sure. Okay, so there is one more application of gauge gravity duality that I really want to talk about, and you have done
Mhm.
some work on it as well. So that application is to understand something called, non-Fermi liquids. So first of all, can you tell our audience that what are non-Fermi liquids, and how can the gauge gravity duality help us to understand, the behavior of non-Fermi liquids?
Absolutely. So to understand non-Fermi liquids, we first should understand what a Fermi liquid is. Okay. Okay. So let's do that. Let me ask your listeners, or encourage your listeners to think about a very general question. Imagine that you have a bunch of matter. Okay. Take a pile of matter, and now imagine cooling it down to very, very low temperatures. And now let's ask what happens to that matter. Okay. Now let's try to think about the minimal ingredients that we have here. When I say a bunch of matter, I'm actually imagining that there's a conserved density of that, there's a conserved number of particles. Okay. In quantum physics, whenever you have a conserved number of particles, that means you must have a symmetry associated with that. In the simplest case, if you have like a pile of electrons or something like that, then you have what's called a U1 global symmetry. Okay. Now, if you take that system with a bunch of particles that you can count with a U1 symmetry, and you cool it down, it turns out that in normal physics, there's sort of only two very obvious things that can happen at very low temperature. Okay, again, whenever I say only, I always immediately think of the exceptions. But in normal textbooks, you learn about two sort of things that can happen. Okay, if you have these particles, okay, and if they are fermions, then when you cool them down, you have to start thinking about the following fact. Because the particles are fermions, that means that no two particles can ever be in the same state. Okay. Now, normally in quantum physics, the way that we think about particle excitations is by going to what's called momentum space, which means that we basically think about each particle in terms of its momentum. Okay. So if two particles are fermions, then no two particles can be in the same state, which means that if we have a particle at momentum equal to zero, the next one must have non-zero momentum, the next one must have a different momentum, and so on. You can imagine making a shape in momentum space and populating all the states. And because no two particles can have the same momentum, roughly speaking, the number of states that are occupied, okay, traces out some shape in momentum space. And this shape is the edge of the shape is what is called the Fermi surface. And this is what you get if you read any textbook on what happens. This is basically what's happening in metals, where the electrons form a Fermi surface. Okay. And this is basically the most normal thing that you can imagine for a fermion. And now what you can imagine doing is you can imagine turning on a small interaction between these particles. Then these particles will now interact with one another. But it's a remarkable fact that this Fermi surface idea is not greatly modified if you turn on a small interaction. The particles still interact with one another, but these particles now, the interaction is what's called irrelevant. It does not really matter at long distances. And this is what now is called a Fermi liquid or a Landau Fermi liquid. This is the sort of basic way to understand the physics of electrons in metals. Okay. And just for your readers, I want to advertise this idea for those of your readers who, or, sorry, listeners who know about effective field theory. I want to really advertise a beautiful paper by Joe Polchinski called The Effective Field Theory of the Fermi Surface. It really explains this fact that I told you. It tells you, it gives a really beautiful, simple understanding of why interactions are irrelevant around the Fermi surface. It really helps you understand why electrons in a Fermi liquid are weakly coupled in some sense. Okay, that's an aside for the technical listeners. But this is what a Fermi liquid is. It's basically electrons at low temperatures.
And
Now,
before you go
yeah,
on,
yeah.
before you go on, so this can be a bit confusing for some of the listeners. So it's called a Fermi liquid, but it also, describes metals, which are solids. Is that correct?
Yeah, that's a good point. No, absolutely. So the reason why it describes metals, which are solids, are because the electrons within the metal basically move
Mhm.
freely, right? An
Right.
electron may appear solid to us, and it's solid, but the electrons slosh through it freely. And you can imagine there's a sea of a liquid of electrons moving through the metal. Yeah, that's a really good point, which I should have mentioned.
Okay.
Absolutely. Yeah,
Okay.
good. Yeah. And so
So,
that's a Fermi liquid. Okay.
mhm. So
And this is sort of something that we understand quite well. And now you can ask, is that it? Is that all that we can understand? And the answer is no, because in real life, there are plenty of examples of things that are not described by Fermi liquids. And because they're not Fermi liquids, we call them non-Fermi liquids. Okay, it's a sort of strange discussion. Anything which is not a Fermi liquid is a non-Fermi liquid. More specifically, what people normally mean is they mean a system of particles whose microscopic constituents are fermions, whose physics does not appear to be weakly coupled at long distances. That's what people would call a non-Fermi liquid. And I would say the most dramatic example of that is the high TC superconductor. If you take a real life material called a high temperature superconductor, and if you heat it up, then what happens is you lose the superconductivity at high temperatures. But when you lose the superconductivity, you get something which should be kind of like a metal in that it has a liquid of electrons sloshing around. But that liquid of electrons does not behave like an ordinary Fermi liquid, and so people call it a strange metal. And I would say that's maybe the most I'd say the most well publicized non-Fermi liquid. This thing.
Yeah, I mean, I was actually coming to this the topic of strange metals. So, what are some of the most well-known properties that are different for strange metals as compared to ordinary metals? For example, is there some difference in resistivity or something else like that?
Yeah, precisely. So I think the most well-known thing is indeed the resistivity. So if you look at a non-Fermi liquid, then you can do a sort of simple calculation. Sorry, if you look at a Fermi liquid first, let's do the first, the ordinary thing. Look at a Fermi liquid, then you can look at how electrons sort of scatter off of each other, and you can do a fairly simple calculation that convinces you that the resistivity of this Fermi liquid should go like the temperature squared. Okay. And okay, that's fine. Now, again, I recommend those people who are interested. I recommend this paper by Joel Polchinski, where he sort of convinces you that on very general grounds that this resistivity really goes like t squared. Anything that's like in a sort of in this Fermi liquid universality class. And then if you imagine looking at a strange metal, the experiments show that the resistivity does not go like t squared. Instead, it goes like the temperature. It goes like T. Okay. And this is the most dramatic difference, I think. It goes like T, and it goes like T over a large range of parameters. Okay, it's a very robust phenomenon. It's not some accident. And so it would be really good, that's the most dramatic example, I think. It turns out all other transport phenomena also display all kinds of strange behavior that you don't expect from non-Fermi liquid. Again, the details escape me now, but you can measure all kinds of things, and most of them are not like what you expect from a weakly coupled non-Fermi liquid. There's something very interesting happening there.
What is transport phenomena?
Transport phenomena basically means resistivity is an example of a transport phenomena. To measure the resistivity, you apply voltage, some current flows, and you measure it. Okay, that's transport because some current is flowing across the system. You can measure other things. Heat is transported. Things like that. You can put a magnetic field and then apply voltage this way and measure the current the other way. It's a sort of off-diagonal conductivity called the Hall conductivity. You can measure all of these things. They're all different sorts of transport, and in strange metals, they're all sort of weird and different, basically.
Right. Okay. So how can holography help us to understand non-Fermi liquids?
Yeah, so that's a fantastic question. So what holography does is, let's imagine that we wanted to study the same problem using this holographic duality. What you do is you imagine taking a density of stuff, okay, and then putting it at some finite temperature and then cooling it down and then looking at what happens. And so each of these steps is very simple to understand in a holographic duality. A finite density of stuff means that you have what's called this U1 global symmetry, which really just means that you have a symmetry. And we know how symmetries are realized in this AdS-CFT duality. It turns out if you have a U1 symmetry, you have something a lot like an electric field on the gravitational side. Okay? And if you now sort of crank up the density of this U1 symmetry, say I have a finite density of particles, that means the electric field becomes large in the interior and it points in the radial direction. It points through the full geometry and goes all the way to the edge of the geometry. Now, if you say you put it at finite temperature, what that means is you have a black hole in the interior. In fact, normally we set it up so that our black hole is sort of flat. It's like a flat black hole. I should probably call it a black brain and not a black hole, but that's the idea. You have a horizon, which exists in the geometry. And then finally, when you turn the temperature of that and make the temperature very, very small, then what happens is this geometry kind of stretches out in a manner, it becomes very, very, very long in the interior. And so you have a very, very long geometry with electric field sort of piercing through it. And then we now have a system which is a finite density of stuff, okay? And this stuff is strongly interacting with itself. And you can ask now, is this strongly dense, this strongly interacting density of stuff, what is it? Can we understand it using normal field theoretical techniques? And it turns out that I think it's fair to say that we really can't. It's not a weakly coupled density of stuff. It is, for example, not a Fermi liquid. Okay. So this finite interacting density of stuff forms an example of a non-Fermi liquid. And that's, I think, what sort of drove a lot of attention in this. It gave you an example of a strongly interacting density of particles, where again, we can calculate things where the interactions are strong. And it's a new starting point to try to understand strongly coupled phenomena.
Right. Okay. I see. Okay, so before we leave this topic of holography, there is one more topic that I want to address. So,
Mhm.
in the gravitational duals of some, CFTs, now CFTs are conformal field theories, right? Uh, I have seen that some people use these higher spin gravity theories. And
Yeah.
at first, it was kind of surprising to me because there is this theorem by Weinberg and Witten that you cannot have, higher spin particles without having some contradictions. So first of all, I want to ask you that how do these theories, for example, there is this Vasiliev theory that people use. How do these theories evade something like Weinberg-Witten theorem? I think, and you can also tell our listeners what is Weinberg-Witten theorem. And the second question is that why are these theories important, or why are these theories useful to have gravitational duals of CFTs?
Yeah. So okay, so let me address the second question first and then come back to this. So first let me to listen, what is a higher spin theory? So first, before answering that, I want to talk about a different question, which is sort of what it means to be free. What is the meaning of freedom in the particle sense? Now, what I mean is, imagine that you have a theory of particles, okay? And imagine that they don't interact with each other. That's what it means when we say free theory. It means the particles don't interact. Okay? Then that means if you start with two particles here, then they'll just move through each other without interacting with one another. If you have three particles, then they'll again just move through each other and so on for arbitrarily many particles. And what that means in a technical sense is that all the information that you have about where the particles sit, it's very easy to project it backwards in time. And that means technically that there's many, many conserved quantities, okay? Roughly speaking, the momentum, of each particle is a conserved quantity, okay? So there are infinitely many conserved quantities. And there are many ways to organize this information. This is now just a bit technical, just if you're technically minded listeners already know some quantum field theory. One way to organize information is you have a massless field theory, call phi your field. Just take a bunch of derivatives of phi, okay? D mu one, D mu two, D mu three, derivatives of phi. The equation of motion is box phi equals to 0. So that means all of these derivatives of phi are divergenceless. So you have infinitely many conserved quantities, okay? And the number of derivatives sort of counts the spin of the part of this object. And so you have many, many, many higher spin conserved currents, okay? This is just a fancy way to say nothing happens in a free field theory, okay? Okay. But now you can ask, is there a gravity dual for such free field theories, okay? Or almost free field theories? And let's think about what the gravity dual should tell us, should involve. The gravity dual of this theory needs to include all of these infinitely many conserved currents, okay? The way the duality works, if you have a conserved current that maps through the duality to a massless field living in the bulk, whose spin is the same as the spin of the conserved current. So what we conclude is that for the dual of a free field theory, there should be infinitely many massless fields in the bulk with higher and higher spin. This is an example of what's called higher spin gravity, okay? And it's actually very, very complicated. You have infinitely many fields, all of which are massless, and they interact with one another in the bulk in a very intricate way that was figured out by Vasiliev. It's called the Vasiliev theory in higher in most reasonable dimensions. And this Vasiliev theory, is the dual to a free field theory. And in a sense, it's so complicated because the free field theory is so simple. in general, in duality, there's some sort of conservation of difficulty. If one side is simple, the other side should be hard. Free theories are very simple, so the other side of duality is insanely complicated. Okay? And I think the place to get started thinking about this, if you, for your listeners who are, again, technical, is this very nice paper by Klebanov and Polyakov explaining how what's called the ON vector model, which is the free theory with n components roughly, is dual to this Vassiliev theory. Okay, so that's what higher spin gravity is and why you want to study it. Let's remind ourselves what the Weinberg-Witten theorem's content is exactly. If I recall correctly, it's
Sure.
something like, yeah.
So it says that if you have spin 1 particles, then if you have a particle that has higher spin higher than 1, then it cannot have a conserved a stress energy tensor, something like that, or conserved current, something like that. So it's kind of like a no-go theorem for having particles which have a spin higher than 2. I've talked to some people and they say that the fact that you have an infinite number of particles is something that goes against the assumptions of Weinberg-Witten theorem. So I don't know if that's a satisfactory answer or not.
Yeah, I think there's a couple of ways to think about it. Now, we should again, I've forgotten the details of the theorem. So you see, there's a couple of important things to note, which is that number one, these theories only really make sense in anti-de Sitter space. So the Weinberg-Witten theorem, I think the kinematics that is used in that is specific to flat space. So that's one thing. But I think I'm missing the point actually. If I recall correctly, the Weinberg-Witten theorem, doesn't that sort of tell you that you can't have massless composite particles? Is that correct? That in a non-gravitational theory,
That's an implication of it. I think
yeah,
that's an
that's
implication of it. Yes.
yeah, that's right. Now, I don't think, you see, I seem to recall, again, I'm reluctant to say imprecise things lest I confuse your listeners, but I seem to
I mean,
recall that
we can skip the question if you want. It's fine.
yeah, no, it's okay. Let's talk about it, and then you can decide whether or not your listeners should be inflicted with
Sure.
my musings. Now, if I recall correctly, you see, I thought the Weinberg-Witten theorem actually has a problem with the spin 2 graviton as well. Is that correct?
Mm-hmm.
And the resolution of that, I think, is that the stress energy tensor, which couples to that graviton, is not actually gauge invariant under diffeomorphisms, and in some sense is not an exact object. But you see, not an exact thing that you can think about. But you see, even gravity has an issue with the Weinberg-Witten theorem. So I think the Weinberg-Witten theorem already doesn't apply to normal gravity with only a finite number of fields, because the graviton count, because the fact that the stress energy tensor in gravity, meaning stress energy tensor meaning the nonlinear interaction of the graviton with itself, I think that already contradicts the assumptions. And so the Vassiliev theories and so on all definitely have an interacting, gravity sector. You cannot decouple that gravity sector. So I think that's another way to think about why it doesn't really apply to the
Okay, I see.
to Vassiliev gravity. Yeah, but again, you should. I don't want to tell you readers things that might be wrong, but I seem to recall something like that. Yeah.
Sure. Okay.
Yeah.
Okay, so another topic that I want to talk about now is the topic of generalized symmetries. I think, and you also have worked on it, and you also have notes on generalized global symmetries. So for the audience, can you give a brief description of what are generalized symmetries? And when I say generalized symmetries, I am talking about higher form symmetries and non-invertible symmetries, both of them. And if you want to talk about higher group symmetries, you can. And the second question is that why are they important? I mean, there has been a lot of work done on these symmetries in the last 10 years or probably more than that. So, what kind of problems become, easy to track, easier to solve at least, using generalized symmetries?
Mhm. Absolutely. So this idea of generalized symmetries is in a sense it's a relatively new thing, but the idea is really simple. Okay. So again, in normal physics, we often think about physics in terms of particles. Okay, and you have a bunch of particles, they move around, they do their thing. But if the number of particles is conserved, then we know that there's this thing called Noether's theorem, which basically tells us that whenever we have a conserved particle density, there's a symmetry associated with that. Okay, we've talked about this already a little bit. If you have a conserved particle density, then you have a U1 global symmetry. Okay? This is a fine thing that everyone learns about early on in their quantum mechanics or quantum field theory education. Okay, but in real life, there are other things than particles. Okay, in physics, in quantum field theories, and in real life in general, there are other objects. So, for example, you can have strings in many real life systems. I'm not talking about string theory. I'm talking about really mundane systems. Like, for example, electrodynamics, okay? Normal electromagnetism, the first theory that we learn about. It actually has two kinds of string in it, right? It has electric field lines, which are strings, and it has magnetic field lines, which are a different kind of string, okay? They move around, they do their thing. And these strings, in the absence of any matter, these strings are conserved, meaning that they can't end, okay? And a really natural question is to ask, what is the symmetry principle that protects the conservation, not of particles, but of higher dimensional objects like these strings, okay? And these are now understood. The name that we give to such symmetries is higher form symmetries. Higher form symmetries are the symmetries that protect the conservation of extended objects, so strings, membranes, and so on. And there are many, many physical systems with such objects. Anytime you have such an object, you probably have a higher form global symmetry lurking around. So that's why they're so important, because they give you a very precise, very symmetry-based way to think about all kinds of problems appearing in many interesting systems. Okay. And so that's what's called a higher form symmetry. The higher form here just means that if you write down the formula, the conserved current for this, it's a differential form that has an index higher than 1, so it's a higher form symmetry. You can just think that the high there talks about the dimensionality of the object that you're counting. Okay? So that's a higher form symmetry. Do you want me to give a brief explanation about non-invertible symmetries
Sure.
as well? Yeah. So non-invertible symmetries are they're sort of they're conceptually different from this, I would say. And a non-invertible symmetry, maybe an example of this is the following thing. Imagine you have a normal symmetry. Okay, if you have a normal symmetry, then you have a number of particles, and you can count the particle number. All right, let's just think in detail. How do we actually count the particle number? And we count the particle number by imagine that our system lives in space and time. What we do is we do an integral over the system at one time, okay? And it's an integral that fills all of space. We do an integral, okay? And that integral is done at a fixed time slice, and it sort of counts how many particles there are at that time, okay? And then it's the whole point of having a conserved particle number is that you can count it later or count it earlier, and it counts the particle number and you get the same answer. Now, normal symmetries are called invertible, or we don't even say it, it's just assumed that normal symmetry is invertible. And what that means is this object that counts the number of particles, it acts on all the fields in a particular fashion. It acts in a way that's invertible. In the simplest case, for example, if we're just counting a normal particle density, it will rotate my fields with a U1 phase, okay? And you can always undo that rotation later by acting with a symmetry that operates the other way. Now, here's a question. Can you imagine having a setup where you can keep one of these properties but not the other? Meaning you can count something which is the same, meaning you move it upwards in time or downwards in time, you get the same answer. So it's sort of counting something, but it's not invertible. Meaning if you act once, you cannot undo that by acting later. Okay? Is such a thing possible? And it turns out it is completely possible. It happens, and again, in a lot of very interesting, very simple physical systems. And it's a very useful idea. So that is a non-invertible symmetry. It's a kind of generalization of the idea of symmetry in that something is conserved, but it's certainly not an ordinary symmetry in that once we act, we cannot unact and get back to where we were before. Okay.
Right, which means that these symmetries do not form a group, right?
Yeah, exactly. They don't form a group. It's a fact. This is a fact we have to live with. They don't satisfy the group axiom. They satisfy a more complicated thing. If you take two of them and sort of fuse them together, then you get some other object outside, which is not. Yeah, okay. Let me not get into it. But it's not. There's no simple group action of these things. Yeah.
Right. So what kind of structure these symmetries form if they don't form a group?
There's a lot of work done in classifying the representation theory of these, but roughly speaking, for me, intuitively, I like to think in as lowbrow a way as possible always. If you have a group, if you take two of them operators and you fuse them, then you get one more thing again, which is the thing labeling it is the same in a sense. You take one group element, another group element, fuse them together, and you get another group element. Now, this fusion is not enough. You won't generically get just one thing. If you fuse two things together, you will get a sum over many symmetry generators. Okay, so it's a kind of fusion algebra, and there's numbers that characterize that algebra that you can think about.
Right. Okay. I see. So what kind of problems have become easier, using the ideas of non-invertible symmetries?
Yeah, so I think it's fair to say that basically any problem where you have extended objects. So this includes a lot of things that we really know and love. So for example, one thing that I really liked when I was first learning this field was the issue of confinement in non-abelian gauge theory. Let me just remind your readers what I don't know why I keep saying readers. Let me remind your listeners
Right.
what confinement is. So if you imagine that you have a non-abelian gauge theory, meaning a system of particles that's described by gauge theory like QCD in our world, then you can often take two particles in this theory, okay, and try to separate them. And if you try to separate them by a long distance, what happens is that you have what's called a flux tube, a kind of stringy object forms between these two particles, okay? And as you try to pull it apart, the tension in this thing is constant. So you have to apply more and more and more energy to pull these particles apart, which means basically that you can never really separate these two particles. These particles are always bound to one another. And this is the phenomenon of confinement. Okay. Now, when I first learned about confinement, I found this though the mathematics is not really that complicated, somehow where to put it in your understanding of physics is a bit confusing. Okay. Because if you think about things like the phases of matter, then there are phases of matter that are sort of very simple, like solid, liquid, gas, things like that. There's more exciting phases of matter as well, like superfluid, things like this. But they all involve symmetries that are spontaneously broken or unbroken or something like that. There's what's called the Landau paradigm that tells you how to think about all these phases of matter. And let me not explain the whole thing to your listeners now, but basically, if you think about ordinary phases of matter, those you learn about in your undergraduate, you can really think about them in terms of their realization of symmetry, called the Landau paradigm for the phases of matter. And when you learn about confinement, you feel a little bit uncomfortable because it doesn't fit into that. Okay, it just doesn't. It's a different thing. There's no obvious local order parameter for confinement, and this feels both cool and uncomfortable in some deep sense. And what higher form symmetries tell you is that actually the phenomenon of confinement is also a symmetry breaking transition. It's a symmetry breaking phenomenon. But the symmetry you want to think about is not in terms of a normal symmetry, but instead in terms of a higher form symmetry. Okay. So you have confinement when a higher form symmetry is unbroken. That's what we call confinement. And you can sort of anticipate this because I talked about these flux tubes. These flux tubes are strings, and so there's clearly a higher form symmetry involved somewhere. And it's very interesting because you learn about confinement, you learn sometimes there's an order parameter for confinement, sometimes there isn't, this sort of area law and things like this. And all that stuff is very transparent for higher form symmetries, and in fact is in direct analogy with what happens for normal symmetries. That's conceptually very useful. And calculationally, once you know that, then you can really push on this and learn all kinds of beautiful things. A lot of beautiful work done with confinement, expressing it in this new language and often deriving new results using this language.
I see. Okay, so there's one more, you know, a realization of these, I don't know, yeah, non-invertible symmetries. But that will lead us to another thing that I want to talk about. So uh, there is a very well-known duality in physics called the Kramers-Wannier duality in the Ising model. So does that also fit into the paradigm of non-invertible symmetries?
Yeah, absolutely. So just again for your listeners, let me remind them what the Kramers-Wannier duality is. So one of the most studied systems in physics, I would say, is what's called the 2D Ising model. And let me just say what that is briefly because we will need it. The 2D Ising model is the following. Take a two-dimensional grid, a two-dimensional square lattice, and at each site on the lattice, put a classical binary degree of freedom. We sometimes call them classical spins. Classical binary degree of freedom means that it can be either +1 or -1. There's one bit of information at each point. Okay. And now couple these guys together. So each spin only talks to its nearest neighbors. Okay. And do it in a way that preserves the symmetry, where if you take all the spins and you flip them all. Okay. So if all the spins are +1, you can flip them all to -1, and that preserves the symmetry. That's a Z2 symmetry, Z2, because you can flip everything and couple them together in a way so that you preserve that symmetry. And that system is called the Ising model. It has a single coupling, which couples together the spins with its nearest neighbors. And that's one of the most well-studied systems in physics. It has very interesting things going on. And in particular, it has what's called Kramers-Wannier duality, which is the remarkable fact that if you take this system at very, very low temperatures, okay, and it turns out to be the same as the system at high temperatures. There's a precise mapping of temperatures which maps the high temperature to the low temperature phase. Okay. And this is a very, very deep fact. It happens again for other deep reasons. But what it means is that if you have a system, this Kramers-Wannier duality system, you can, in a sense, think about it in two distinct ways. You can think about it at one temperature, or you can calculate most things, almost all things, I would say, from the same system at its dual temperature. And when one of them is low, the other one is going to be high. Okay. Now, this duality is an amazing thing, and let's sort of push on it a little bit to understand what we can do with this. So, in particular, the 2D Ising model has a phase transition. So, if you cool it down to very, very, very low temperatures, then all of the spins want to be aligned with their neighbors. And what that means is basically all the spins are going to be aligned. So, if one of them is +1, they're pretty much all going to be +1. If one of them is -1, they're all going to be -1. That's called the ferromagnetic phase of the 2D Ising model because all the spins are aligned. And now, if you crank up the temperature, okay, then the spins start to fluctuate more and more and more. And at some point, you lose this ferromagnetic order. The magnetization is lost because they've all fluctuated too much. The disorder has destroyed the magnetization. And now all the spins are kind of randomly doing their own thing, independent of their neighbors. That's called the paramagnetic phase. Okay? And the ferromagnetic phase and the paramagnetic phase are connected by a phase transition about which we know quite a lot. Now, what I want to talk about, and again, this might sound a little bit intricate, is what is happening at this phase transition point, what is the Kramers-Wannier duality doing that I told you about? Remember, it maps high temperature to low temperature, but high and low means above and below the phase transition. And it turns out at the duality point, at the critical point, the Kramers-Wannier duality maps the system to itself again. So it's a self-duality, okay? It's a change of variables you can do in the system which keeps everything the same. And because it's a duality, there's a sense in which you can think about it as a symmetry. And again, in the distant past, if you thought about this as a symmetry, you'd probably get very confused. But in fact, it's been known for quite a long time. In fact, even predating all the recent explosion of interest in non-invertible symmetries, it's been known for quite a long time that you can think about this because it's a symmetry. You can imagine gluing together the sort of system in one duality frame, with the system acted on with the duality. You can imagine gluing them together. They get glued together along a line, and you can now move that line however you like, and nothing really changes. And in that sense, it's like a conserved quantity because you can move it up and down, nothing changes. And it's what's called the non-invertible duality line. It turns out it's a non-invertible symmetry in the way that I mentioned it earlier. So that was a lot of words for your listeners, but indeed, the Kramers-Wannier duality ties very, very nicely with this non-invertible symmetry.
So one thing that we didn't mention earlier, I think we should have mentioned that. I think, and if we did mention that, I think this comment wouldn't be so surprising. The thing is that these higher form symmetries or symmetries in general are often thought of as being, associated to, these. I don't know how to say this without using a lot of jargon. Well, codimension p+1, something like that, operators, right? So, the thing that you talked about is, a line, and we're talking about two-dimensional Ising model, which means that it's codimension 1. So, do you want to extend to that particular comment? Because I think that comment, this particular fact will make, this fact about the Kramers-Wannier duality less complicated.
Yeah, absolutely. Indeed, you're right that I should have mentioned the dimensionality earlier. So this is often in the new way of thinking about symmetries, you hear the word topological thrown around a lot. And this can seem intimidating, but it's really not. You see, whenever you have a conserved quantity, remember I mentioned that if you have some particles, you can count them at one time, you can count them at a later time. Now, this is a fancy way of saying this, is that there's a topological operator in your theory. By topological, I just mean you can move it and nothing changes. Okay, so you have a conserved charge, you can move the whole thing up, you can move, and nothing will change. In particular, you can imagine curving your charge operator so it no longer sits on a flat manifold, but is rather on a curved manifold, and again, nothing will change. So there's a sense in which whenever you have a symmetry, you have a topological operator in your theory. And the dimensionality of the operator is what determines whether or not it's a normal symmetry or a higher form symmetry or something like that. So for normal symmetries, we count particles, and we do that by integrating on a time slice. Now, a time slice is one dimension less than the full number of space-time dimensions. So in the lingo, we say it's codimension one, okay, meaning there's one extra dimension. You can move it around in one extra dimension. Codimension two means that you count strings. Codimension three means that you count membranes, bedsheet type objects, and so on and so forth. Now, if you now therefore think about a normal symmetry in a system that has two space-time dimensions, then that normal symmetry involves integrating over all of space, but space is now one dimension because the other dimension is time. And so therefore a normal symmetry in a two-dimensional system involves integrating something along a line. And that's why I mumbled some words about topological lines when talking about Kramers-Wannier duality. It is a non-invertible symmetry, but it's in a sense a non-invertible symmetry that is not higher form. That's a lot of jargon, but it's a non-invertible symmetry that has the same dimensionality as normal symmetries. Okay, that's why it's a line. And any listeners who are listening to this purely on audio without the video, I realize will not have seen my hand motions, but I claim they add something to it. So yeah.
Sure. Okay, so I mentioned before that the topic of Kramers-Wannier duality will take us to another detour,
Yeah.
and that detour is actually using machine learning. So you recently wrote this paper where you used machine learning to rediscover Kramers-Wannier duality using a map which was parameterized by the parameters of a neural network, I think.
Yeah.
So, can you tell us about a bit about that project, and do you think that this particular approach that you took can be used, to solve some other problems as well?
Absolutely. So maybe again, let me just say a few words about machine learning in general, maybe before getting into the specific project.
Sure.
So recently I've been spending more and more of my time on machine learning problems. In particular, this year I'm in fact on sabbatical at the University of Amsterdam, working almost completely on machine learning problems. And I think this is a very interesting way to think because, in a sense, the philosophy of machine learning is that in the olden days, if you wanted to write a computer program to do something, you would write the program, right? You would write something like if, like you say you want to read handwriting, you'd write something that looks at the pixels and be like, well, if there's a pixel that's on like white next to a pixel that's black and it does this and does that, then that's a nine, and then otherwise it's a five, or so on. So you'd write a lot of if. I'm not really sure how you do this, to be honest, in a programmatic sense, but you'd write something yourself, trying to figure out the logic on how to make the thing happen. And you see that the machine learning approach to doing this is completely different. You don't write anything yourself, or sorry, you write things yourself. What you do is you just sort of write your problem as a function. So if you want to, for example, read handwritten digits, you imagine the existence of a function that takes in an image and spits out the digit that you want. Okay, so there's a function that takes in a grid and spits out a number. And then you parameterize that function in the computer in a suitably flexible way. So this is where neural networks come in, but the neural networks are just a way to parameterize the most general function on a computer in terms of simple building blocks. So you do that. You write it in the computer in some fashion, and it turns out you can do that in a simple way. And then you tell the computer, find the thing that does this well. The computer will amazingly just do that. It will do that for you. It will find the function does that well. And this works amazingly well for all kinds of problems, as I'm sure everyone knows now. It's amazing what you can do with this approach. And so I just find that very, very interesting. It almost suggests that if you can only parameterize what you want to find in a way the computer can understand, then the computer will find it. And so that was what inspired this project. So now should I tell your listeners a bit about what the project actually does? Yeah. Okay, so the project that Hassan mentioned is the following thing. Whenever you have a duality like the kind I just mentioned, this Kramers-Wannier duality, what's really happening is that you have a physical system which you can think about in two different ways. Okay, in other words, you have one Hamiltonian and you have another Hamiltonian, and these two Hamiltonians, which are different, somehow describe the same physical system. Okay, and in particular, we call it a duality when given every observable on one side, you can figure it out from the observables on the other side. There's a mapping from observables one to another. All right. So a duality consists very formally of the following thing: two different Hamiltonians and a way to compute observables from one side from the other. In other words, a map observables on one side to the other side. Now, there are very complicated examples of duality. For example, the AdS-CFT duality we talked about in the first half of this conversation. And the Kramers-Wannier duality is a much simpler one. All the ingredients are much simpler. And the question that we set out to ask was, is there a way to discover this kind of duality using machine learning? In other words, can we parameterize the map between observables using this neural network machinery? And can we parameterize the most general Hamiltonian and try to find, for a given Hamiltonian, both a dual Hamiltonian and a dual mapping of observables? And so this is a very well-posed problem. And we did this. Basically, we take data, we simulate on the computer, we simulate the 2D Ising model, and then we throw that data into an appropriate system that uses a neural network to try to represent that data in a different fashion and find a different Hamiltonian. And we showed that you can reproduce the duality that we know and love, this Kramers-Wannier duality. You can rediscover that using this approach. So in particular, the temperature on one side is mapped to the other side, and this very simple neural network basically finds that mapping of temperatures. And it also finds the mapping between observables, where of course we knew that mapping is a really well-known thing, but we rediscovered it using the computer. And so in some sense, this was just a toy exercise to try to see if this could be used to discover dualities. And we did manage to rediscover the existing one. And now the really fun thing is, can we use it to find new dualities? Are there new things that we can do with this? And that I don't know the answer to, but we're working on it right now. There's technical obstacles with this. It turns out that the technical problem that we're solving is a numerically difficult one, but I believe that they can be solved. So we're now trying to make our technical side stronger so that we can try to look for new dualities.
So the fact that you already knew about Kramers-Wannier duality, does that fact play a huge role in this work, or does that not play a huge role?
So we tried things where it didn't work at the beginning, and we kept pushing on it until it did work. And if we had not known that there was something that we were looking for, we probably would not have kept pushing on it, right? So in some sense, it does. It's the motivation. So that's why I think that there's something a bit sleazy about when machine learning rediscovers something. I mean, in a sense, you knew it was there. So it's not really a big deal. So I want to stress that our work is not a big deal. It's fun, but it is not very dramatic. We knew about Kramers-Wannier duality. It will be a big deal if we can use it to find something new that we did not know about before. Then it will be a big deal. Yeah. So,
I see.
yeah.
So, and another quite famous duality is something called the duality between the Sine Gordon model and the Thirring model. So can you do something like that with the approach that you used?
Yeah, I think so. I mean, basically, if you want to, the approach that we used will work for any lattice type system. Okay. So if you can find the discretization of your duality and simulate it, then in principle, the machinery works actually. Now, in practice, it will become very we're already struggling so our system has only these Z2 degrees of freedom. And even then, we are struggling to generalize to more complicated things. Like if we add too many couplings, then the optimization procedure does not converge anymore. And so even with these Z2 degrees of freedom. So in practice, if you want to do this for a system which has, for example, a U1 global symmetry, so a natural next target is particle vortex duality, which is not the same as the Thirring model, but at least it also has a U1 symmetry in it. Then if you want to do things like that, then you need to first get the numerics to be more stable. But in principle, the conceptual side should work. Now, the Sine Gordon Thirring model that you mentioned is a bosonization type duality. And I'm actually not certain to what extent we can reproduce that precisely in the continuum. Sorry, on the lattice, I mean. This is a well-known thing, but not to me. Yeah, do you know exactly how that works on the lattice? The Thirring model?
I'm not sure actually.
Yeah. So it's a little bit intricate because a key aspect of that duality is the fact that you have so again for your listeners, the Sine Gordon Thirring model duality is an example of bosonization, which basically says that if you're in 1+1 dimensions, then in some sense, because particles just move past each other in straight lines, that's the only thing they can do, the sense where bosons are the same as fermions. And so you can sometimes write a bosonic system in terms of a system of fermions and vice versa. And the Thirring model is a model of fermions, and the Sine Gordon model is a model of bosons, and somehow they are dual. Okay. Now, a key role here is played by the structure of the conserved currents. In other words, there's a left moving current and a right moving current for the particles. And it's important that you get that exactly right and that you get the anomalies between these things exactly right. And that's the kind of thing that's often a little bit tricky to do on the lattice. So I'm a little bit nervous about discretizing that system. This is the problem before applying my machinery. I think first I want to make sure that there's a discrete version of the duality that works well. And this is surely known to people, but I can't immediately recall this. I know my colleagues in Durham have done work on discretizing various related systems. So
Right, right.
once we can discretize it, yeah, there's probably if we can discretize it cleanly with no sign problem in a way that we can simulate in a nice way, then the machinery should apply if we can get the machinery working in a robust way. Yeah,
I have one reason to believe that probably
yeah,
this discretization doesn't exist, and the
yeah,
fact that motivates this claim is that in the Thirring model, so Thirring
yeah,
model is a model of fermions, right? It has chiral
yeah,
fermions in it, and
yeah,
there is this theorem called the Nielsen-Nonimia theorem that you cannot put
yeah.
chiral fermions on a lattice. So probably
Yeah,
that's
yeah.
why you
The,
cannot put it on
indeed,
a lattice.
indeed. The simplest thing does not work. That's definitely correct. Yeah. However, there are fancier things that you can do that, again, if I recall correctly, there are fancier things that you can do that do preserve the left and the right. They preserve the left and right moving symmetries, but and the anomaly in some restricted sense, without without breaking the theorem. And so this is the field
Hmm.
of active research right now, actually. People are working on this right now. This is a new thing. So in particular, my colleague Tin Suleiman Pasic has done work on this, as well as many others. So, but indeed, this is what you state is exactly why I was nervous about doing the discretization. When I said there's left and right moving currents with an anomaly, this is exactly the reason why I'm a bit stressed out about this. Yeah.
Sure,
So,
sure. Okay.
yeah, yeah,
I see. Okay, so I have one question about the neural network itself. So
yeah,
uh, I'm not very familiar with the kind of methods that people use to, the machine learning methods that people use to study physics. So
yeah,
correct me if I'm wrong on something. So the simplest neural network that people study is something called the feed-forward neural network, right? In which the previous layers can affect the next layers, but not the other way around. But there are some architectures called, for example, the recurrent neural network or the transformers, where the other thing can happen. I mean, the next layers can affect the previous layers. So do you think that these kind of architectures can be used to solve some problems in physics which are not tractable using feed-forward neural networks?
yeah. Absolutely. I mean, I think that the using the right architecture is super important in applying all of these things to anything. So again, let me just provide a little bit of background. So I mentioned earlier that the way all these things work is you try to write your thing in terms of the most general function. Now, so if you were really thinking about the most general function, then this is what you would do. You'd basically put in write a system that takes in a vector. Your data is a vector, okay, and then a sort of standard feed forward network acts on that with a matrix where generically all the entries of that matrix are non-zero. But it has many components, okay, and those components mix all the data together in that vector. Then you act on it with a non-linear function that acts on each component of the vector, okay, and then you do that whole process over and over and over again. There's a lot of matrices, okay? And all these matrices basically scale like n by n, where n is the size of your data. Now, if your data is kind of small, that's okay. But the whole point, of course, is that your data is generically very big, okay? So what I just described is a normal feed-forward network with all the entries in this matrix being non-zero. So a key thing you want to do is think in your data, what is the right sort of neural network to use, okay? So for example, I talked about a handwriting example, and handwritten digits that are often studied are small enough that you can do this. But really, if you're trying to recognize an image, you don't want to use a feed-forward network because the feed-forward network takes your image data and compresses it into a giant vector and throws out all information about the locality that was present in the original thing. What you want to do is use a neural network that knows about locality, that knows about translational invariance on the picture. And that neural network that you use in this particular case is called a convolutional neural network. I mentioned it because I think it's simpler for physicists than the other two things that you mentioned. And a convolutional neural network is basically, instead of taking the whole thing and doing everything to it, it incorporates translational symmetry into the network. It sort of consists of a series of filters where the filters move across the system. Okay. And in most in some physical applications, you want to do that. So for example, in our work, we didn't really call it that because it's so simple, but what we used is not really we didn't use a fully connected network. It doesn't take in the whole data of the lattice of spins. Instead, it looks at a small neighborhood and manipulates that. So it's more like a convolutional network than it's like a feed-forward network. Okay. And so we needed that from the very beginning. If we hadn't done that, there's no hope anything would have made any sense. And so the art of choosing which problem to use for which network to use for your particular problem is really important. And it's always ongoing. So for example, recurrent networks, where in the past, a recurrent network is sort of something that incorporates locality in time. So you feed in a time series, and what it does is it looks at a particular time and a little bit in the past, and it doesn't look at the whole time series, and then it moves that thing forward. So that kind of thing is sort of probably the right thing to use if you're looking at something that has a fixed time window. A transformer is a more recent architecture which has been very useful. It's behind things like ChatGPT that everyone knows about. It has a sort of specific architecture that lets different things. It's sort of I'm not going to explain this very well because I'm new to this field and therefore I've not built up my explanations very well yet. But it basically lets different parts of the input signal attend to one another. It's called an attention mechanism that figures out which parts are important for a given question and then weights those appropriately. And again, this turns out to scale very, very well and is behind all these recent amazing advances in language models that can talk to you and so on. So to recap, I've just been explaining all the architectures, and I think there's a lot of scope for using these things to do different things. Physicists are quite aware of this. I mean, if you look at the work that's being done, people are using architectures that solve the problem in the right way. So people are definitely aware of this, and I think it's quite open what can be done with this. This is evolving very, very quickly. Yeah.
Right. Okay. So I'm sure you know about a discovery that was made in, if I'm not wrong, in the late 70s, which is called the four-color theorem, right? The four-color theorem in maths was, solved using a computer. And then when that was done, some mathematicians like Michael Atiyah were saying that, yeah, I mean, you can, prove it, but I think that doesn't mean that you understand. So
Yeah.
the question is that we are in a new age, and suppose that if we do, make some discovery using machine learning, what should physicists, feel about that? Should they accept it without understanding it properly themselves, or should they, have a very skeptical view of it?
They should have a super skeptical view, I think. I think that
Mm-hmm.
the way I imagine this working is that the computer might give you some some input, but I think that the whole fun of it is for the human to understand what's happening in humanly explainable terms. I think that that's necessary for us to really appreciate the beauty of it. With the four color theorem, if I recall, there were some edge cases, right, that the computer had to solve. Is that right? I never really
I mean,
studied this.
I think it went through
Yeah,
all the possible cases and proved
right.
that it holds for all the cases.
Indeed, but some humans figured out these are the cases that have to be
Yes.
studied,
Yeah.
and
Exactly.
then the calculation involved, the computer verified that, but it verified it in an algorithmic and airtight manner, right? There was no uncertainty in this. It just checked them. So maybe to me that again, I don't know details of this because I never studied that theorem, but to me it's more like using Mathematica to do your algebra. Like you should do an integral, you use Mathematica to do the integral, and if you had to do 1,000 integrals, it would be crucial to use Mathematica to do each of the 1,000 integrals and not do them all by hand. But
Right.
the computer is not, it's doing a very controlled thing for you. And if we're going to use machine learning for physics discoveries, then I think I cannot but think that the human has to understand everything that happened, completely. Like imagine that my approach works and I discover some new duality. Okay, then we have to understand why that duality is there. Kramers-Wannier duality is there because of a deep fact about order and disorder. If you have a system with a global symmetry, then you can represent that so in a sort of twisted way, in that the thing that was ordered on one side is the thing that's disordered on the other. In a sense, that is the deep fact of Kramers-Wannier duality. And if my approach works and I find some new duality that doesn't fit into that sort of simple framework, then we have to understand the physical principles behind that duality. That's where the actual fun part will start. So I think that the humans should be super skeptical of computer stuff, and we should use the computers to give us more choices to have more chances to have fun, not really, not to take away the burden of doing the fun stuff from us, I would say.
Right.
Yeah.
I mean, I was thinking about this example, and I came across this argument that someone may give. Someone may say that if you look at the work of Kramers and Wannier,
Yeah.
they stumbled upon the existence of this self-dual temperature, right? Self-dual temperature. But they didn't understand the phase transition itself that was done later by Onsager. So even when
Yeah. Yeah.
humans work on these things, they don't understand
Yeah. Yeah.
everything. So that's fine
Yeah.
if
Yeah.
machine learning gives you some results. So what do you think about that argument?
Yeah, yeah. I don't think that there's I would say that I'm not sure that that argument is different. Like I agree with that as well. I think like maybe a way to think about it is imagine we discover something. Like imagine we're like poor Kramers-Wannier. We know about the duality, but it doesn't occur to us that the phase transition is happening. But in an era of computers, of course, we would have known that transition is happening because we would have simulated it, right? And
Mhm.
moved to the transition and found it, and that would have been the key missing thing that would have let us understand how the duality interplays with this thing. So I think that's fully consistent with what I'm saying, that the computers will help surely, and they can help nowadays. They can help in new and exciting ways that they couldn't before. But I think that the results always have to be explainable in a human fashion, I would say. So,
Okay. Okay, so we have half an hour, so I think
yeah,
let me go through the rest of the questions. So one thing that I want to talk about is that how can we tackle a lot of misinformation about high energy physics that is being spewed on the internet? So there's a lot of high energy physics misinformation on the internet, and I think I'm sure you recently know about the recent arguments that were happening on Twitter as well. So how should we as a community, how what should we do to tackle the misinformation? Because the thing is that this misinformation has a lot of undesired consequences. I think I also said this in the last two podcasts as well, probably, that I know some students who are much younger than me who want to pursue high energy physics or more specifically string theory, but they're afraid to say it because they think that their peers will make fun of them because they're just brainwashed due to all of this propaganda. So what should we do to tackle this propaganda? Can we tackle this propaganda? Is it too much?
yeah. So I mean that's it's a really good point that you make, and yeah, I'm also very bothered by this, to be honest. I'll just say why I'm bothered by it so much before we get into what we should do about it. Is that I don't think it's really done in good faith, and I think that it spreads some. You see, it a lot of this takes the idea that everything is wrong, everything high energy physicists are doing is a waste of time. They're they're evil and they're doing this to get grant money or some strange thing like
Exactly.
that, disconnected from reality. And I just it really bothers me that this is a message that is being given to young people everywhere because it's just not true. We all try to figure out the things that we're interested in. We work on them as hard as we can, and it's very baffling to imagine that we are deliberately misleading everyone for some nefarious purpose. It's very confusing, and also I don't really like any viewpoint that says that you should not learn something. You should not learn string theory because blah blah blah. You should not learn this because blah blah blah. It's really not a good viewpoint. You should be encouraged to learn things. The best, if you're not sure about a subject, the best way to make up your mind is, of course, to learn it. You have to learn it to decide, see what it's really saying, and then you can decide whether you think it's a useful way to attack the problem or not. Now, so time is finite, of course. We also make decisions what to study, but I really don't like this thing, like what you mentioned with your colleagues, that people are being told, don't learn this because it's bad. This is a terrible thing. And what we can do to combat this misinformation, it's tricky because I think it requires effort. To be honest, I think it requires effort and talking. So recently, I decided that I have some tiny videos on YouTube that are mostly just recordings of talks that I gave elsewhere. But I think I'm going to personally try to do a bit more and try to follow in the footsteps of amazing people like you and try to like give sort of some short videos myself on things that I think are interesting from my own point of view. And maybe others could also do this to provide counter voices of the bits that are actually beautiful, that are actually important. And maybe that's a sort of positive way to try to counterbalance this, rather than saying, this is wrong, that person is not saying something I agree with, but to rather instead say, here is a beautiful thing that has come out from this subject. And here is why I think it's important and beautiful. Here's another beautiful thing. Here's something we've learned about the universe from this side. maybe it's just time for us to do things like that, and that has the two benefits that hopefully it helps can help, but also it's fun, and it's a I think a good thing to do, as I'm sure you know. It's a good thing to do in general. So that's my take. That's what I'm going to try to do. And what about this is a question where I think I'm justified asking you. What do you think should be done on this?
I think the thing is that my vantage point is very different as compared to a vantage point, the vantage point of people like you, because I'm a PhD student. I don't have a permanent job, right? So if I had a permanent job, then I think I would spend a lot of time. I think I still spend a lot of time doing this. I should spend less and do more work on my research. But I would have spent a lot of time, in uh, okay. Answering directly to the criticisms, however bad they are, coming from the other side. Because the thing is that um, it's probably true that we will not be able to counter all of the misinformation because there is too much of it. But the thing is that the presence of a counter narrative is better than having no narrative, counter narrative at all. I mean, even if that counter narrative is not able to debunk all of it, because the thing is that. The impression that goes into the public is that they are silent because they don't have any answers. That's simply not true, right? We have
Yeah,
answers, we just don't care to put that out there in public. I mean, or probably we don't have time to do that. So I think the presence of a counter narrative is important, even if that counter narrative is not as strong as the misinformation. So, and someone may say that, okay, these are just a bunch of words. Yeah, I know, but I think these can be put into some concrete practices. So yeah, if I had a permanent job, then I would probably do it. But right now, I'm doing what I can do, but there's a limit to what I can do. So yeah, of
indeed.
course, I need help from people like you or some other people who are working on the subject. But yeah, I think there's a limit to what one person can do when it comes to debunking. When it comes to spreading misinformation, I think there is no limit to what one person can do because that's much easier, I think. Yeah.
Right. Yeah.
Um,
Let me say, just by the way, I mean, clearly you're doing a lot. This is I'm very happy to be here on this thing that you're doing. I think you're already doing a huge amount. And so, yeah, then I guess indeed it is for the rest of us to step up a bit.
sure.
I think. Yeah. Yeah.
Well, even this criticism about grant money that you referred to. So in my
Yeah.
previous episode, I was talking to Zohar Kumar Gotsky, and we talked about the same topic. And he said that, and he said something which should be intuitive to other people as well, but I don't know why it is not. That if physicists are actually interested in money, why don't you just go to finance and use your skills there? I mean, it's much more money there as compared to grant money, for example. So I don't know what is the counterpart in the UK, but in the US, the two biggest funding bodies are NSF and DOE. The money that you can earn from NSF and DOE, Department of Energy, is peanuts. I mean, if you really want to make money, you can go to something like Wall Street. I don't know what is the counterpart in the UK. So why would you be in the business of making money using grant money? Um, and the thing is that this particular criticism actually resonates with people. I don't know why does it resonate. So do you know why does it resonate? And can
Yeah.
you back me up on the fact that there is not a lot of money if you really wanted to steal grant money? I mean, it's not a lot of
Yeah.
money. You can
I
make
mean,
much
and
more
also
money.
just to be clear for everyone, when we get a grant, we don't get that money. Like the grant is money, but what we do with that money is that we give it to we hire people, we hire PhD students, we use it. It does not come into our pocket. That's not how grants work. So it's very confusing. It's very confusing. If you want to have a job with a high salary, indeed, if you have a physics background, you probably want to go into finance and not try to work your way up through UK academia hoping that there'll be a high, that's just not really how it works. And I don't really know why it resonates. I mean, I think that let's see. Yeah, I don't really know why it resonates so much. I mean, you see, maybe it resonates because you see, it is continuously connected to other things, which is that in science funding, one can ask, how should money be distributed? Which fields should money be distributed in? And this is a very reasonable discussion that should be had, but it needs to be had in good faith. It's not, it's not, that's not the way that I see these discussions going. It is not that any scientist in any field chooses to be a scientist because they want grant money. That makes no sense whatsoever. So I confess I don't really see Yeah, I don't really know why it resonates, but I'll stress when you get a grant, you don't pocket it. The money goes to a university office, and then you use that money to do science. In string theory, in theoretical physics, we don't really have any equipment expenses, so we use that money to hire PhD students who then get PhDs, postdocs, things like that. Yeah.
Or go to
So,
conferences, for example.
or go to conferences, indeed. But that is that's really honestly a kind of a small part of it's a
Small part
tiny
of it.
tiny bit of the grant. Yeah, yeah. So
Right. I
yeah,
mean, the thing is that this kind of narrative does include does attract a particular kind of audience, which is the the science deniers. I mean, we cannot do anything about them, but for a
yeah.
lot of other people who are not science deniers, for them there is another talking point that can pull them in, and it is the fact that they are using our tax money to do science, which is not even good. So probably that's one reason why a lot of people are attracted, due to this kind of talking point. But I'm not sure, what attracts them.
Yeah,
Um, right.
yeah.
I mean, the thing is that we are so used to accuse politicians of stealing our money that a lot of people don't even see a difference between accusing politicians and accusing scientists, of stealing their money. Although, if scientists were stealing their money, it's just a tiny amount of money, but they're not stealing it. Anyway.
Yeah, one thing I should have looked at before coming on this, which I did not, was it would be interesting to, it's all this plain discussed, but we should look at the numbers, how much goes into theoretical. I think I saw it flashed on Twitter at some point. You should talk about how much money goes into theoretical physics research of all sorts, not
Mm,
just high energy, but of all sorts, compared to anything. I think it would be good to have some perspective on how much that is. I should have looked up these numbers before coming on this thing, but I do not think it's a very high percentage. But again, yeah,
sure.
yeah, yeah.
I mean, I do remember that some months ago, probably a year ago, the CEO of OpenAI, Sam Altman, he said that we are building artificial intelligence. I don't care if it takes 500 million or even more. I was thinking that what would happen if somebody doing fundamental physics would have said that. People would have said that, okay, yeah, that's clear evidence that they are just stealing our money. So in some in some fields you can say that, because
Yeah,
people
yeah.
think that, okay, you're doing good work, but in some people's the propaganda is so bad that you can't. I mean, of course we don't need something like 500 million. I mean, when it comes to theoretical physics, probably in experimental physics, but in some fields you just can't say it because people are just already primed to believe that you are stealing their money. So I don't know what to make of that particular example. Okay. So I have one more question, then I could go to people's questions. So people sent you some questions for you as well. So the question that I want to ask you before going to people's questions is that what factors do you take into account before taking a PhD student?
Yeah, so this is tricky. So we of course I look at the CV and all of this stuff. In Durham, we have a sort of group interview process where we all interview together, all the students. This interview process is pretty important for me. I really like to see. It's really hard to get a feeling for how students think about problems without seeing this interview. So the interview is important. I look at, I'm aware that grades are an imperfect metric, but of course, I do look at the grades. But I think that one can make up for mediocre grades through strong performance on the interview, because the way that we do the interview is really we ask students to talk about what their projects have been on in the past, and then we ask them to solve a problem on the board. And it's the problem is designed so that it's not super easy to solve, and so you can really try to get a feeling as to how students think from how they attack this problem. And so I really want to see that. I want to see how students think, that they have a good solid thinking process, and that they're enthusiastic about it, because we should face it. It's hard. It's hard, and the thing that you really need to get through the stuff that's hard is enthusiasm. You have to be really enthusiastic about it. That goes an extremely long way. If you don't have the knowledge you need, you can acquire the knowledge you need, but it's harder to acquire enthusiasm. So I want to make sure students are enthusiastic.
Do you have any tips for younger researchers for what to do when, okay, I mean, it's very hard, it's very unlikely for people to pursue a PhD in theoretical physics if they don't have motivation and enthusiasm. But the thing is that the PhD is hard. It requires a lot of patience. So it can happen that your motivation dies down during the PhD. What to do? Do you have any advice for that?
Yeah. So first, I'll just say, I mean, this happens. It happened to me, multiple times. It happens to everyone during the PhD. I think it will definitely die down. And so it's I don't think there's a one size fits all thing for this. I think if you're stuck in a concrete technical thing, it's good to check if you're stuck in a technical thing. really, articulate very carefully, really, really carefully why you're stuck. So for that, it's very helpful to go talk to your colleagues because, like, which I mean other students or other professors, because to explain your problem to someone who is not working on it with you will both remind you why your problem is interesting and force you to think about it very hard. So you can explain the details to them. So I think that's very helpful to talk to someone about it. So that's something within physics itself. And more, this is maybe a bit cliche, but it's helpful to get out of the, take some time for yourself and do something fun. It can feel like you shouldn't do that when you feel like you're behind, but it's really not true. You should go on a small holiday, spend time with your friends and family. These things genuinely. This is again sounds cliche, but it's true. They genuinely do reboot your brain a little bit. You'll feel better about life. You feel better and go back.
Sure.
And the third thing that helped me is just remember that you're part of a grand tradition of solving insanely hard, insanely interesting problems. Your problem doesn't always feel very interesting to you, but it's very interesting. And the only reason it doesn't feel interesting to you at this moment is because you've been working on it for a while. Just remind yourself of that. You read a popular science book to remind yourself that this is, that you're part of an amazing tradition. It's a great thing to be part of, and it's meant to be hard. So yeah.
Right. I mean, I can vouch for the fact that when I was younger, the advice that you were giving, I mean, spend more time with your friends and family times like this. When I was younger, I did find this advice to be cliche, and I was like, yeah, that doesn't work. But as I'm growing older, I mean, it makes more sense to me. Yeah, I can vouch for this
exactly.
fact.
Yeah, exactly. Yeah, again, I'm sorry for giving cliche things sounding like a self-help book, but it is true. Sometimes the
It
cliches are
works, yeah.
correct. Yeah, it works. Yeah.
Okay, one more question is that, so I mean, there can be many different reasons for the motivation to die down. One reason can be that you worked on a project for probably some months or sometimes a year, and then it failed. How to get back from that particular experience? I mean, I don't know if you
Yeah.
went through that, but probably you have seen someone who went through that. So that happens to some people. So how to
Yeah.
get
Yeah.
back to from that experience?
Yeah. So first, you say I don't know. Of course, I've gone through this. I mean, I'd say most of my projects don't. Yeah. So
No, no,
some
in your
large
PhD,
fraction of things that I
in your
think about. Oh,
PhD.
my PhD. Yeah. No, PhD as well. Yes, that's right. My PhD as well. Certainly. Yeah.
Okay.
And again, some large fraction of things just don't work. And I think that it's you first of all, it's I think unlikely that of course a project can fail, but it's unlikely in a theoretical science that you do not get out of it, that you don't get anything out of it. It's unlikely for that to happen. You see, you will have understood some branch of stuff that was at the edge of knowledge, and most likely within that branch of stuff that you've understood, there's something that you will use. Maybe it leads you on to your next project. Maybe you just learn something about something else, and I think it's very unlikely, I would say, to actually have a complete, a complete failure in that sense. So I think that's one thing. But despite that, it doesn't get away from I think the deeper question, which is that how do you persevere in I mean, I think it's unlikely a project will fail completely, but nevertheless, you will encounter in your life as a scientist many things that will feel like failures. Sadly, as an academic, you'll apply to a million things, and a lot of that million, some fraction will not work out the way that you want it to. And I think to get back to it after that, to keep motivated, is kind of the same as what I said about losing enthusiasm. Just remember, you're part of a grand tradition. It's a good thing that you're doing, and it's meant to be difficult. You're doing something that's very, very hard. It is meant to be difficult. If it wasn't difficult, you probably wouldn't be doing it. That's part of what drew you to it in the first place. So just I'd say remember that.
Okay. Okay, so I had one more question, but I think we are running out of time. We have only 17 minutes. So I have a lot of people's questions. So let me just
Okay,
throw those questions at you and you can answer them, briefly so that we
sounds
cover
good.
all of
Yeah,
them.
yeah, 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 yeah,
Okay,
yeah.
so the first question is that what is the relation between, and if some question, the answer to some question is long, you can let me know and I can save it for the end if we have
Okay,
time. So
yeah.
the first question is that what is the relation between string theory and the 3D Ising model, and what are the open problems?
That's a great question. Okay, so very briefly, in the 3D Ising model, people know about the 2D Ising model. 3D Ising model, you have a bunch of spins living on a 3D lattice. And it's interesting to think about the boundaries between a bunch of up spins and a bunch of down spins. That boundary is a two-dimensional world sheet, okay? And it's two-dimensional, meaning you could try to study it with string theory, okay? So in particular, people have tried to do this. Polyakov's book has an amazing account of this. His book, Gauge Fields and Strings, which, by the way, I highly recommend. Amazing book. Everyone should read this. It's beautiful, profound. It has some, towards the end, it has some great chapters on this, on trying to build the string theory of the Ising model. So there are many problems with this, of which one of them is that the string theory that describes the 3D Ising model. Sorry, I should just say, by the way, the 3D Ising CFT is not solved. We know a lot about it. From the bootstrap, we've calculated many, many, many amazing properties of it. We can simulate it, but it is not solved, meaning we don't have a satisfactory theoretical description of it away from the bootstrap. And so you might think that using the strings to describe it would be a good thing to do. In fact, one of the reasons I think string theory was invented was partially keeping this problem in mind. But it's hard because you see the strings that describe the 3D Ising model appear to be very strongly coupled. The way we do string theory from the world sheet involves a sum over genuses, involves a string coupling, and that string coupling is taken to be small. For the 3D Ising model, it does not appear that the string coupling is small. There is no reason to believe it to be small. In fact, I wrote a paper with John McGreevy where we tried to add something to the 3D Ising model to try to tune the string coupling to be small artificially. This was insanely fun, but it did not work. In that when we tuned it to be small, we entered a new phase where string worldsheets filled all of space and ruined the Ising transition that we wanted to study. So this, as far as I'm told, is an open problem. I think that this is a good problem. This is an insanely hard but interesting problem to study from the point of view of modern string theory. It's not been studied in a long time, and I think that there are fun things one could try to do with this. Good.
Okay, and just so you know, we have 15 more questions, and we have 15
more
minutes.
questions. Okay, good. So that means I'm going to answer each question
under. Sure,
in 30
a minute.
seconds. Yeah.
Yeah. Okay.
Okay.
So in your generation of theoretical physicists, were there any standout individuals that you noticed?
Yeah. So there were, of course, many, but I think I'm not really going to answer that question in that way because I don't really want to pull particular people and put them on a pedestal, even though many, many people who I had the fun of interacting with have gone on to do amazing things and continue to do amazing things both in and outside of physics. I think maybe what a good way to the person who asked that question, I think the fun thing to do is to find the standout people in your generation and hang out with them and learn from them. I think that's the thing. Yeah.
So, in your view, what separates the good physicists from the brilliant physicists from the very exceptional physicists?
So again, that's tricky. I'd say in a really short thing, I think the all physicists should really calculate well. Very exceptional ones have a sense of poetry about their ideas. They don't just do technical things, but they see the universe in a poetic and beautiful way. And so an example of this, I would say Polyakov's book is an example of poetry that happens to be written in equations. Yeah.
Okay. So it's not more it's not a question, more like a comment. I just want to thank him for organizing the recent online school on QFT as part of ICDP's Physics Without Frontiers initiative. It really helped me a lot. Okay. So it's not a question. So how does I think we have covered that question. Okay. There's one question. How do I sell generalized symmetries to phenomenologists?
Yeah. I would say first of all, maybe don't try to sell it too hard. Just approach them and ask them what problems they're working on that are interesting, and see if you can help them with their problems. That's what I would say, instead of pushing it on them, because pushing a topic on someone else doesn't really help. But maybe you can actually help them with their problem. That's what I would do.
Okay. So can you ask him to upload more physics videos on his channel? The first one on his YouTube channel was the first video on his YouTube channel was amazing, and I find myself going back to those QFT lectures constantly. So it's just more like a request.
Thank you. I will. Yes. That's it.
Okay. Well, it's about your father. It says that his father, Dr. Jafar Iqbal, is a great man. What kind of things he learned from his father?
From my dad and from my mom, I learned too many things to mention. But I think that they were my first teachers. They taught me the importance of working hard, but also the importance of being a nice and kind person to everyone. And I cannot say what I've learned from them in 30 seconds. So I'll just leave it at that.
Sure, of course. Okay, so it's again a request. It says that please organize a gauge gravity workshop for third world countries. I don't know if you have already done it, but it's like a request.
Yeah.
Okay.
Well, I'd love to. Yeah. Yeah.
Okay. So, what is the importance of internships in theoretical physics undergrads?
Internships, I'm going to interpret that as being meaning research, and I think it's very important if you can to do research, mostly because it gives you a taste of what is happening, and also gives you someone who will write a letter of recommendation for you that will go into depth about the things about you that we want to know when looking at your application. So I would do my best to do some research in your undergrad if you can. Yeah.
Okay. Is it compulsory to have publications before PhD?
No, definitely not. Yeah. Yeah.
But most probably you know that there is a rumor in young people that you have to have publications, right?
Yeah, there's a rumor. So it will help your application stand out, but I don't, it's not compulsory, you know. The thing that happens when you have a publication, though, is that it means that you worked probably with a professor in some length, and they've also written a letter explaining in some detail as to your capacity for doing research. With that information really does help. So don't stress out if you don't have a paper, but do try to do research, and that research need not be in HEP-TH. You can do something else as long as the person writing the letter will explain how you think and say nice things about that.
Sure. Okay. So it says so now you can take more time because I think we'll make it. So you can
Okay,
take 2
good. Yeah,
minutes. That's fine.
yeah, okay,
Okay.
yeah,
So
yeah.
are there any examples where generalized symmetries are the only way to compute things?
Oh, only way is always a bit strong because you could always ignore the symmetry and just calculate, in some brutal way.
Right.
But there are things where the conclusions would be very hard to get without them, I think. So this I cannot explain in a minute. But let's see. So yeah, I feel like I can't do that question justice in a minute, but I'll point to some recent works on sort of the understanding the phase structure of gauge theories, where generalized symmetries and their anomalies were crucial. You wouldn't have gotten that without knowing that. I think that's a really good example of something that you wouldn't have gotten without generalized symmetries. Yeah.
Okay.
So
So there's another question that was part of the earlier question about selling generalized symmetries to phenomenologists. It says
yeah.
that does non-invertible symmetry bias something that can keep the experimentalists busy? And you can take more time because we have time now.
Yeah. I'm not aware of an immediate consequence of a non-invertible symmetry that we didn't already have some inkling of in other from some other context. I mean, experimentally checkable one. Let's see. Yeah, I'm not at the moment. This could be my own failure of understanding, but I'm not immediately aware of a smoking gun thing. There has been a fair amount of work recently at the intersection with phenomenology that uses nonverbal symmetries to organize calculations, and it's possible that some of those calculations could be useful for phenomenology, but I'm not immediately aware of one. Again, I'm probably not, despite my work on nonverbal symmetries, I'm not enough on the pheno side to really answer that question really well. I encourage you, Hassan, to have someone on the pheno. Maybe you already have on the pheno side who can answer that question better than me. I'll say, for example, in my own work, I can talk about that. And for example, there were some numerical simulations that had results that were not in agreement with hydrodynamics. That was very confusing. And it turns out they're in perfect agreement if you use the higher form formulation of hydrodynamics. I found that very nice because we wouldn't have gotten that without the higher form symmetries. But that's a numerical simulation, it's not. And there have been other numerical simulations as well. That's not real life, So I'm not aware of a smoking gun signature in real life yet. But fingers crossed. Yeah.
Okay. So I think this is the second last question. The question is that you have done your PhD you have studied in MIT, right? Which is in the US, and now you
Yeah.
are in the UK, right? So
Yeah.
in the US, you're not supposed to know your PhD project before you apply, but in the UK, it's the other way around. So do you
Yeah.
see any advantage of one system over the other?
Yeah, I think I want to correct a misconception about the PhD project in the UK, in that you don't have to know your PhD project before you apply. The application process in theoretical physics involves writing a research statement, and a lot of people really stress out about that.
Mhm.
But you shouldn't if you're in string theory or high energy physics, you shouldn't or high energy theory anyway, you shouldn't interpret that as meaning that you have to write a reasonable research proposal that you will then work on during your PhD. That's not what it's for. We know that you can't really do that as an applying undergraduate. It's more to explain your enthusiasm and talk about what you like and what you don't like and what you know and what things like that. That's what it's for. So I would say that's not really, you shouldn't think you need to know your project going in. Most people don't, I would say.
Mhm.
Now, there are, however, big differences. And part of the thing is that in the UK, the PhD is significantly shorter than in the US. And this does play a role. I think there's no denying that this does play a role. And it means that in the UK, you do need to be pretty organized. In the US, it's quite normal to like just kind of, take classes slowly, talk to everyone in the first year and not do as much. In the UK, you don't want to do that. You want to be calculating stuff pretty much from the get-go. And that is
Okay.
a big difference. Yeah.
Okay, so this is the last question. It's a bit vague. The question is that do you have any advice for undergrads, masters, and PhD students separately?
Okay, let's see. Undergrad first. I think undergrad, it's great. You're learning stuff. Your only job right now is to learn stuff. So, enjoy it. Learn everything that's in your courses. Also learn things that aren't in your courses. I know it's hard because you have exams and stuff, but try not to let the exams define you. Read around the things. Take every problem set as an opportunity to calculate something where you will get feedback on it. It's amazing. So that's what I'd say during undergrad in terms of career. During masters, it's a little bit in the middle, right? You're sort of transitioning in some sense. So again, it's in the middle, sort of, but I think the philosophy should be similar to your undergrad. One thing maybe that's different is that you will probably have a thesis project in your masters, and I would say take that seriously. I'm not sure, you might not always have a lot of control over what you work on, but in a sense, it doesn't really matter that much because almost everything is interesting at that level. So take that seriously. Really try to get to know your supervisor well. And again, that's both because take it seriously, you'll have fun with it. It's more fun if you take it seriously. And also because if you decide you want to go for a PhD, the supervisor's input is really helpful for us to know what for us to read your application and know what you're saying. And finally, for the PhD, this is a much bigger thing. You're in it for the long haul, and again, take it seriously. Try to understand everything. At the beginning, I'd say go to all the seminars, do all these things. At the beginning, you won't understand any seminars. That's okay. You're not meant to understand the seminars. At the beginning, you are just meant to know this is what people work on, and this is you're learning how to give a talk. You're also probably learning examples of how not to give a talk from these seminars, and these are important things. And just make sure you're part of your culture of your group. Hang out with them, have lunch with them, learn what everyone thinks about, how they think about problems. Talk to your friends a lot about your colleagues in the department about physics. This is really helpful to learn what they know and to explain to them what you're doing. And of course, work hard and write papers and all that stuff as well. But you already knew that. You were doing that already.
Sure. We have 3 minutes. I think I missed one question,
Okay.
so I think you can address it, then we can wrap it up. So it's very common for PhD students to, deal with imposter syndrome. How to deal with imposter syndrome?
I don't think that there's a great one-shot way to deal with imposter syndrome. I think that one thing that can help, maybe, again, this is hard to do, but one thing that I think can help is to try to forget about yourself for a bit when you're working. Don't ask yourself, am I smart enough to do this? Because you're definitely smart enough to do this. Instead, ask yourself, where is this minus sign coming from? Or whatever. Why doesn't this integral converge? Don't ask yourself, oh my God, why am I so dumb that I don't know how this integral doesn't converge? That's not a useful question. The useful question is, why does it not converge in its own right? Think about the science and not about yourself. Ideally, you enter a state where you are not really there. It's just the science, and you sort of forget about your own feelings about the science and just do the science. That's a great state to be in, and I encourage you to try to be in that state as much as you can. And at that point, imposter syndrome kind of goes away because it's not interesting anymore. The science is what's interesting, and whether you are or not an imposter is no longer the important question anymore. The science is the important question. If you can enter that state, that's great. It's hard to do, but I claim it's possible. Even in the depths of imposter syndrome, it's possible to enter that state. So I think that's the best thing I can say.
Okay, so Dr. Iqbal, well, thanks a lot for your time. It was great to talk to you, and probably we can talk again sometime soon.
Absolutely,
So
and thank you. And I want to say, I really, you are amazing. This was an amazing experience because you were extremely well prepared, and you guided the conversation in a way that I think was very good for the readers. So clearly, I've only listened to one or two of your podcasts. I'm now going to go listen to all of them. They're clearly, they're clearly very good, and I think a great resource. The few that I listened to were a great resource to the community. So thank you for doing this. I think
no problem.
I and everyone else really appreciate it. So yeah,
my pleasure. Okay, thank you so much.
All right,
okay,
take it easy.
See you
Bye.
then. Bye. So if you like this video, give it a thumbs up and consider subscribing, and the YouTube algorithm thinks that you will also like this video.